The following presentation, entitled Sampling and Nested Data in Practice-Based Research, was given by Zyzanski, Ph.D., on September 25, 2008, as part of the 2008 Practice-Based Research Seminar Series at Case Western Reserve University in Cleveland, Ohio.
Okay, welcome everybody to our PBRN seminar for this evening. I want to introduce our guest speaker. It's really a great privilege to introduce Dr. Steve Zyzanski. Steve has been on the faculty here in the Department of Family Medicine at Case almost since the beginning. I think he was Dr. Jack Medalley's first hire, and Dr. Medalley said one of his very best hires. Steve served as the research director, the director of the research division in the Department of Family Medicine for many years until he decided to step down from that position last year. And the department grew in many ways, and many great things were accomplished under his direction. Steve is a stellar psychometrician and biostatistician, has over 140 publications. But I think that the thing that sets him apart and makes him not just a terrific biostatistician and psychometrician, but one who's truly great, is his ability to explain things in a way that really all of us can understand, and to put things really in perspective in a way that relates very directly to whatever the problem is that's at hand, and he has a special ability to do that. So we're really lucky to have him tonight. Please welcome Dr. Steve Zyzanski.
Thanks, Jim. The next two sessions in this class are going to deal with statistical issues. The first one tonight is sample size in practice-based research, and next week we're going to look at statistical analyses for data derived from practice-based research. And as you'll see from this evening as well as next time, traditional statistical approaches to sample size estimation and the analysis of data, hypothesis-driven data from PBRNs is a little more complicated and deviates a bit from some of the statistical things that I think you've been exposed to. So we're going to start tonight with looking at sample size. Typically in practice-based research, they're called group randomized trials. Sometimes they're called cluster randomized trials. And they're basically comparative studies in which, and you notice on some of these slides I have underlined certain words and phrases, and I want to draw your attention to those. So they're trials in which the unit of assignment are identifiable groups: practices, physicians, schools, cities, countries. So we typically think about randomized trials as randomizing patients, but in group randomized trials, their unit of randomization, or unit of assignment, is a group. And then secondly, the unit of observation are members of the group. So we're going to look at patients within physicians, or students within schools, or residents within cities. There's sort of four unique characteristics to group randomized trials, and we already mentioned two of them. The unit of assignment is the group rather than the individual. You assign different groups to your intervention and control group. The unit of observation, as we mentioned, are members of the group. And group randomized trials typically involve a limited number of assignment units in each study condition. I mean, typically you're looking at an intervention control type of design where it is uncommon to find more than about 20 or 30 group units assigned to intervention and control. You might have 20 or 30, 10 in each, 15 in each. Where you're randomizing patients, you can have hundreds and even thousands randomized. So already this is our sort of first departure. You're going to see group randomized trials in the literature where the number of groups randomized is surprisingly small. And I think you'll sort of say, wow, how can you draw conclusions from 30 practices, 15 interventions, or even 10? And you'll get a sense of the confidence you will have by the way we compute the sample size today, by the way we do the analysis next time. Group randomized trials, where you randomize at the group level rather than the individual, has two important impacts. It impacts the computation of the sample size, and it impacts how we analyze the data. And you will see why in a minute. Data where you have groups randomized and you have units clustered within groups are usually referred to as nested, multi-level, clustered data. Those are kind of all interchangeable. You'll see that in the literature. What you have are patients sort of nested with a physician. So for the rest of the evening and for next time, I'm going to really be talking more about patients nested in physicians, because these are likely to be the randomized trials that we'll be involved with. But whenever you have nested data, there is an implied structure to it. You can think of it as a flow diagram. You have several practices. Within each practice, you have several physicians, and then with each physician, you have a number of patients. You have a hierarchical structure there. Generally, you are gathering data at all of those levels, those multi-levels, which is why it's referred to as multi-level data. So data tend to be analyzed from multiple levels. In a typical group randomized trial, the variable at the second level, at the practice level or the physician level, is where the intervention occurs. Half of the physicians or practices get the intervention and half do not. You'll see that in more detail next time. Here are some examples of nested data. A two-level model would be patients nested within physicians. Data are collected from both at the patient level, which some people refer to as the micro level, and then at the physician level. So you'd be interested not only in patient demographics, patient outcomes, but you'd also be interested in what the physician gender is, how long they've been in practice, where their location is, urban, suburban, and so on. A three-level model would be patients nested within physicians, and then physicians nested within practice. And as we get on in our discussion today about sample size, you'll see that the sample size really balloons out when you go to a third level. But there are other ways of looking at nesting. Time points with repeated measure designs are really examples of nested. In other words, the observations aren't independent, and that word independent, you'll see, is going to play a big role in how we compute sample size. So when you're following patients over time and measuring their blood pressure every day or every week, or serum cholesterol, whatever it might be, those repeated measures are really time points nested within patients. Even meta-analyses are considered nested data, where you have subjects that are nested within studies. So you have European studies, you have American studies. So nesting is common. That's the background. Why are nested data a problem? Well, research has shown that, and this has been known since the mid-'70s. Jerome Cornfield, biostatistician, wrote a paper on this back in 72 or 4, pointing out this problem. And the problem is that patients within a physician or units within a group tend to be more similar to each other in terms of the outcome than they do as patients from other physicians. They tend to be correlated. And this correlation violates an absolute core assumption for virtually all of the statistical tests that we commonly use. When you have correlated data, when patients are nested within the physicians and the patients are more similar within one physician than another, and you'll see how we'll measure that, you cannot do a t-test, a chi-square, an analysis of variance, a linear regression analysis without substantial bias. You can do it, but if you ignore the clustering effect, some rather bad things happen. And yet they look like good things. In other words, what you'll see is that the denominator of the statistical test, whether it's the t-test or the within in the ANOVA and so on, are way too small because of the clustering, and you're calling way too many things statistically significant. The confidence intervals are too small, the effect sizes are exaggerated. You'll see that next time when we do some examples of actual analysis. So this is a big problem. This correlation messes up the calculation of the sample size, and it messes up the statistical analysis. We have to do something different. How do we measure how clustered the data are? How high is the correlation? And we do this with something called the interclass correlation, ICC. And we'll show you how to compute that in a minute. But even mild violations of this assumption, or interclass correlations that appear to be small, can cause problems, and you'll see that in the example that I have. So, for example, you're all comfortable, familiar with correlations, and when you see a correlation of 0.50 or 0.70 and so on, you say it's moderately high. When you look at interclass correlations, high correlations are 0.15, 0.10, so you're way down on the low end, and those things exaggerate the sample size, and they exaggerate the assumption violations in the statistical analysis. So even small violations, and you'll see the conditions in which that occurs. What is an ICC? Well, it can be interpreted as kind of the average correlation between any two patients within a physician. That correlation should be zero. Two patients shouldn't affect one another. My blood pressure shouldn't affect your blood pressure, etc. But it does. And if your practice is more geriatric and more patients in your practice have hypertension, and you address that, your practice style may very well cluster the patients, hypertensive patients that you're treating. It can also be presented as a proportion of the total variance. And I kind of like this one as well, because even though it's small, even though if the interclass correlation is like 0.05, that means 5% of the variance in the outcome measure is attributable to differences between physicians. And I'm going to show you next time a study where those differences were bigger and more important in predicting the outcome than were the patient demographics, the patient blood lipids, and so on. So differences, think about it. If you're doing a randomized trial and you're randomizing patients, the whole process of randomization is to get the two groups equal. And then you look at the demographics and say, they are equal, great. But when you do group randomized trials, that's a different issue. And the physicians, if the interclass correlation is not zero, that means physicians are not interchangeable. And you want them to be interchangeable. You say, look, I have 30 physicians, I want to randomize 15 into one group and 15 into another, and they ought to be interchangeable. It doesn't matter who goes in what group. But if you have an interclass correlation, it matters who go. The better physicians go in the control group and make it look like your intervention isn't working. So these are issues that we have to deal with. When the interclass correlation is zero, this is statistical independence. And in a typical randomized controlled trial where you randomize patients, you can assume that the interclass correlation is zero. When it's 1, it means total redundancy. So if you have 30 patients, any one of those patients represent that physician, and you don't need the other 29. So although it goes from 0 to 1, you will rarely see super high interclass correlations. They will all be down 0.3, 0.2, 0.1. Didn't go. Okay. When you have an interclass correlation that's greater than 0, this clustering leads to a reduction in what's called the effective sample size for a given study. And therefore, if you apply standard sample size formulas, you will lead to an underpowered study. And I'm going to give you an example of that. So, for example, if you draw 20 patients from a physician's practice, and the interclass correlation is 0, you have 20 independent, effective sample size is 20. But if the interclass correlation is not 0, then you have less than 20 independent observations. Well, how much less? Well, that depends on how high that is. The higher it is, the bigger the hit you take. And it's rather dramatic, and you'll see that in a couple of examples. So you can measure the degree of reduction. In other words, you can use standard sample size formulas, and then you can compute something called, half of the people who work in this area call it a design effect, and the other half call it a variance inflation factor. I kind of like this because that's what it does. Remember I said all those denominators tend to be too small. This inflates it back to where it should be, and therefore you get a more unbiased test of the intervention and control. But I've seen more sort of design effects. This is a cool number, and it's one that if one of the things you need to leave here tonight is an understanding of this formula and this concept. So the design effect, or variance inflation factor, it's a number that indicates how much the sample size is to be adjusted due to the clustering within groups. And for a two-level design, this is the formula right here, and I will show it to you a little more in the second slide. This is the design effect formula. It's 1 plus, this is the average sample size, average cluster size. So if you have 10 physicians, how many patients did you get from each physician? Divide by 10. That goes in here. And then the interclass correlation goes here. So if the interclass correlation is 0, that term 0, 1 is 1. But look at what happens here. When interclass correlation is greater than 0, this variance inflation factor increases as a function of the interclass correlation and the number of observations. And you can see that in the formula. So let's say you have 25 patients per physician, and the interclass correlation is 0.1. You still have this is a 2.5, so that's not a small number. Or let's say you have 50 people here, but this is really small. So if this is really small and that's big, you're still going to get a big number. Or if this is small and that's big, you're still going to get a big number. And you'll see that. So there are some strategies. Well, let's just bump the sample size up within, because that's the easiest to do. Going out and get more practices, that's a little more difficult. There's diminishing returns very quickly in terms of what that buys you, and you'll see that in a minute. So small values of the interclass correlation combined with large clusters. So anything that makes that fraction, that multiplicative fraction large, causes this whole thing to be 1 plus something. And that plus something is sort of the percentage of the sample size that's affected by the clustering. So how this is used is to compute what's called the effective sample size. What's that? The effective sample size is what is the sample size as if all the units were independent. So if I have 10 physicians and each have 10 patients, you have a sample size of 100. And I'd like to know, since the interclass correlation is not 0, what's the effective sample size, i.e. the sample size as if they were all independent, because that tells you about the power of the statistical test. You're not testing at 100. You are testing at something less than that. And the higher the interclass correlation, the more that gets decreased. So what you tend to do here is you compute the effective sample size by taking the actual sample size, which you just compute with normal sample size tables. You divide by this inflation factor, and that gives you your effective sample size. And you can do it for the group too as well. So whatever the cluster size is, you can divide by the same thing. Here's an example. Given a sample of 10 physicians, each with 20 patients, you now have a sample of 200 patients. But if your interclass correlation is 0.10, and I've been indicating that's a non-trivial, that would be considered a moderately large interclass correlation. The effective sample size would be 200, 1 plus, the average number here is 20, that's 19 times 0.10. So if you have an interclass correlation as large as 10, and you have 10 physicians and each have 20 patients, you think you're testing with statistical power with a sample size of 200, and you're testing with a statistical power as if they were independent of 69. That's a greatly diminished power base. So it then becomes not surprising that you're not finding statistical differences, because once adjusted for this is really what your sample size is. So what you have to do then is you have to estimate what this might be in your study, in your planning studies, and then I have a cool program to show you here in just a few minutes where you can compute the sample size. This is a table from the literature, and I like this because it has, Chuck Eaton here is a family physician at Brown, and this was a NAPCRAG poster presentation, and when I saw it, he sent me the copy of the poster, and I made this slide out of it. This was a cholesterol education program, and it was a sample size of about 260, but 5 physicians, sample size 260, so about 50 or so per physician. And he computed the interclass correlation and the design effect. This is a very useful table. So I show this to you because I want to encourage you, as you do your practice-based research studies on the different types of outcomes that you do, when you write that up for publication, be sure and mention and cite the interclass correlation that you are receiving and you're computing in your studies. Why? Because for people who want to replicate your study or do something similar in the area, they have to estimate their sample size. And to do that, you'll see you need an estimate of the interclass correlation. Well, I don't know what it is. You might, if you look at some of these things. And then the design effect is basically how much the sample needs to be inflated in order to have the statistical power of simple random sampling. So you see here the interclass correlations. The highest one here is, it looks like 06. Yeah, there are 2 06s, age and weight. But most of them are 0.05 or less. But you have, for smoking status, 0.06 and a design effect of 4. You need 4 times the sample size to test with the statistical power of simple random sampling if you were looking at smoking status with an interclass correlation of 0.06. So the interclass correlations don't have to be very big. Again, though, he had 50 patients for 5 physicians. And when you have a big interclass correlation against a big number of patients, cluster sample size, you are going to get a big design effect. And so, this was a kind of a cardiovascular disease study. But this is very informative. I mean, I'm always on the lookout. I have folders in my office where whenever I run across an article that reports the interclass correlations, I put it in there because I'm likely to use that sometime in the future, particularly. Louise Atchison in our department is just completing a study, 3-year study funded by the CDC in Atlanta. And they're looking at a computer program called HealthWare to look at people sit down in doctors' offices and go through this branching technique and come up with their genetic risk for 6 different diseases, for cervical cancer, for coronary heart disease, for diabetes, and so on. So it's very important that she and that study team, because they're looking at new variables, they're looking at genetic related. I haven't seen interclass correlations for genetic variables in the literature. That's a very valuable service. When they start publishing that data, when they look at that people's perceptions about their genetic risk and whether it relates to whether they come in for screening and so on. We need to know what the interclass correlation is. There are 3 different sites and 41 practices in the sites, and they're in very different places. They're in the Chicago area, Michigan, and Cleveland. So it's very important to publish the interclass correlations. Carl?
I was trying to kind of think through comparing different interclass correlations. So some of this looked kind of counterintuitive, and it makes me curious about what was the composition of the 5 physician practices. So, you know, like looking at gender, I mean, we know that in general, female physicians tend to accrue a greater proportion
of female patients.
So, you know, off the top of my head, but not knowing the composition, the gender composition of the physicians, you think, well, that would tend to be a higher interclass correlation. The age kind of makes sense because we know that as physicians age, their patients also age.
Right.
And so that one made sense. You know, to me, it seems like interclass correlations would be very unstable because, you know, you could have 5 physicians, and if they're all male in a study, then the interclass correlation relating to gender is going to be low. Mm-hmm. But then if you have a larger study and even split your interclass correlation, is that how it flows? Or not?
Well, you raise a good point, and that's why. And I'm going to show you a slide in one of the handouts that I asked you to read. Looked at the short form of the MOS, the functional status, across 6 studies, and they vary. And they vary from almost 0 to 6. But the other thing about this one, and you know, you're pointing out the gender and so on, is you also need to know what the inclusion criteria is. They may only be looking at people over 45 or 50 years of age, in which case then the gender thing becomes more equal when you're starting, you know, because you are looking at lipids in probably an older population. It's not just kind of everybody. And that's very important to be able to, when publishing, to clear it. And usually your first table in a practice-based research study, the very first table you have is a demographic table of who's being studied. You know, what were the inclusion criteria, what was the age range, the percent female, and so on. And that's very important because it helps to interpret these interclass correlations. I mean, if this was just a straight primary care population coming in, I would expect that to be higher, as you pointed out. Female physicians tend to see more female patients. But in the way they recruited those patients into that trial may have equated that, or they may have even gone out of their way to. Yes.
It sounds like the other pre-planning piece to this is that by calculating that design effect when you're writing a grant or doing anything else, if you have your pilot data, it seems to me that when you do this, since you want your table 1 to ultimately look equal, you'd have to go with the highest design effect multiplier for your sample size if possible, so that you can have statistically equal groups on all the things that you want to balance on. Is that correct for your?
Yeah. Did you all hear that? That's a very good comment. In other words, if you are looking at multiple outcomes, you need to compute an interclass correlation for all the outcomes. But your sample size really needs to accommodate the highest one. So the highest design effect will be an adequate sample for that, but it will clearly be adequate for everything lower than that. So if you're looking at multiple outcome measures, and we generally are, we oftentimes look at behavioral changes, we look at screening changes, preventive service delivery, and so on. So when you're designing things, you need to look at your outcomes and get an assessment either from the literature or from pilot work, and then go with the largest one. That's a nice comment. Now, we can compute the sample size a priori, and it basically depends on both the cluster size and the ice. And you saw that from that formula, that variance inflation formula had a 1. cluster size and interclass correlation. That's what goes into the formulas for computing sample size. But what we'll see here is that you can have the same or similar power by different combinations. I love this guy. His name is Rodenbush. And why? Because he is a giant in the field. I have his textbook. I meant to bring some textbooks to show you what some of the more readable ones are. This is a tough area. But this guy, I think he's at Chicago, does something that I really admire, and that is he developed, and I'm sure he had a grant to do this because it's a complicated program, statistical software to compute sample size for clustered data. And then he puts it out there on his website saying, download it to your computer, use it with my blessing. And it's a cool program. I highly encourage you to take your handout sometime during the week, punch that in, and click on he's got lots of things in the website. Optimum Design is what he calls his sample size software. And play with it. Type in different things. For example, you may be limited in the kind of practices. We had a fellow in this class last year, Mary Jo Prince Paul, who is looking at quality of life in patients at end of life in hospice. And you're not going to have a lot of group sites. You're going to have a limited, even if you go from Cleveland to Akron to Canton. So if the number of sites are limited, then you have to look at the other parameters to get the sample size that you need. So Rodenbush is, and I'll show you the program, is a really nice software. But this is how you enter the software. See these letters? You will see those letters in the software, so you kind of need to know what they are. So the small n is the cluster sample size, how many patients within a practice. J is the number of clinicians or physicians. Rho is the interclass correlation. This little delta here is the effect size. That's an important number. I'll come back to that. And then these two are kind of the standard statistical parameters.